Hey, everybody who's joining, welcome. We're waiting on Anthony from Aleo to join us. He should be in a second. There he is. How's it going, Anthony? Good morning. Good morning, guys. Good morning. How are you? So we're a little early, so everybody in the room, just hang out while we let people trickle in. We're going to get Anthony set up over here. Sean, can you help Anthony walk through the screen share?
Yeah, for sure. The screen share button is down at the bottom. It says start share. And then I'm sure you're going to want audio. Is it a recording or just normal screen share?
It's just normal screen share, but yeah, I definitely want audio as well.
Gotcha.
Oh, Sean, Anthony's going to be speaking. So if you mean like audio.
Oh, okay.
Yeah, he doesn't need audio track.
He's chilling then. Yeah, perfect.
Yeah, you're good to go, Anthony.
Cool, that's pretty much it. And then you can just full screen it. Perfect.
Awesome.
Okay.
Yeah, let's give people a little bit to trickle in. I'll be right back, guys. I got to run and do something really quick, but I'll be back with you in a minute. We'll officially kick off at probably like 10:01, 10:02. Looking forward to this.
Awesome.
Cool. Just checking.
I like that one.
Yeah.
Slide.
Nice. Thank you. Props to our CEO. He was the one that made the slide, so I'll have to make sure I give him credit before I start.
Oh, there we go. Sure. Love it. Yeah, and what's your role, by the way? Or actually, we'll go through intros here in a sec.
Yeah, sure.
Guess we'll save it. I'm curious. Yeah, actually, what is the last name?
DiPrinzio?
Yeah, DiPrinzio. Yep.
Italian. Are you Italian?
Yeah.
Yeah, I'm actually finishing up the process for getting my Italian dual citizenship.
Oh, that's awesome!
In February, so
yeah. That's very cool. Do you spend a lot of time there?
No, I don't actually. I've been to Italy a few times before, but I actually found out like a couple of years ago I could get the dual citizenship, so I've been like working on it for a little bit, and finally I'm getting towards the end here to finalize it. So
yeah, so my wife is Bulgarian, so we have a place in Bulgaria. We spend a significant amount of time there. We have a 2.5-year-old son. So when he was born, we took him over there and got through the whole process of like the dual citizenship. And I was like, everyone's like, oh, he's got 2 passports. I'm like, yeah, man, we're training the next Jason Bourne over here. Like,
nice. There you go. I like that. Yeah, definitely. If
it's a cool thing.
Yeah. If I'm fortunate enough to have children, I definitely want to pass it on to them, which is something you can do. So
absolutely,
I think it would be cool.
Yep.
Very cocool.
Cool. Okay, yeah, let's just give it a couple more minutes. How's your day, Sean? How you doing today?
Good. Got a nice 10-miler in this morning, so we're thriving.
Bro.
By the way, I did drop in a room chat for anybody over in the audience. Yeah, feel free to drop any questions during the presentation over in the room chat. And yeah, just kind of pick up engagement, but let us know where you guys are coming in from, all that fun stuff. Let us know what you guys are working on, etc.
Yeah, please introduce yourselves in the room chat. As people come in, going to say that basically, a lot of people here know the drill, but for anybody who's new, if you have questions, you have to raise your hand. We'll bring you up on stage. If you're more the shy type, just ask your question in the chat and we'll pick questions from the chat. And yeah, that's it.
Looks cool. Like and would we just do questions at the end, or?
Yeah, I mean, yeah. We don't want to. That's why we have the hand raising function, is so everybody's not like jumping on your presentation. This is yours to roll with, and when you're done, you can signal that you're ready to take questions, and we can get questions from the audience or pull people up and have them converse.
Okay, sounds good.
And this is also being recorded. So for anybody who's not here in the earlier hours, if you're, US East Coast or even Pacific, this is going to be recorded. So we'll be sending out the recording not only to Aleo for your own uses and you, Anthony, but we'll also be posting it on the BUIDL the Earth Hackathon website so that people can look at the recordings throughout the entire hackathon. I'll be sharing the link to join the hackathon if you're not already in there just in a second in the room chat here. That's right here. So you can go there and join. That's the official hackathon registration page. Join there, connect with the Discord, go to the Start Here channel, and everything will make sense.
Cool. Just should I get started or should we wait a little?
Yeah, I think you can roll. People.
Okay.
It's a little. It's on the earlier side, so people usually start to trickle in somewhere in the middle. But like I said, we'll re-announce the recording later on, and yeah, let's just get rolling.
Yeah.
I'm excited to hear this.
Yeah, that's fine. No worries. I think the recording will be the nicest thing to have out of it, just so we can add it as another resource for people participating in the hackathon for sure. Cool. So yeah, hi everyone. Thanks for having me today. I'm really excited to be giving this talk on Aleo, which is the project I work for. Just a quick background on myself. So I'm Anthony DiPrinzio. I'm head of growth here at Aleo. So most of what I focus on is business development, partnerships, talking to developers that want to build on the network, all that good stuff. So I'm not an engineer. However, I believe on December 1st, or maybe I got the date wrong there, one of our lead engineers for our programming language will actually be doing a more technical workshop on how you can actually program in Leo. So if you're interested in that, you should definitely sign up for that event once we get it up on the entree page. But this is more of just a high-level overview of Aleo, kind of how we're differentiated from other ZK-based projects in the space, which I'll dive into a little bit more. And it does have a decent amount of technical information, but hopefully people can get something worthwhile out of it. And before I start, I just want to give a huge shout out to our CEO, Alex Pruden, for these slides. He was the one that originally put them together, so I'm kind of using them for this presentation, but wanted to give him credit for that. And yeah, just to reiterate, like Aleo as a platform uses something called zero-knowledge cryptography. And so I'm not sure how familiar people are with that. We'll go over some high-level basics around that concept, but that's sort of the primary technology that we're leveraging and that you should be thinking about and considering when deciding to build on Aleo. So without further ado, I will get started here. So the first thing I want to address is this concept of ZK EVMs. Maybe some of you have heard of this, maybe some of you haven't. Over the past few months, ZK EVMs have kind of been all the rage lately with a lot of exciting announcements. And so understandably, there's this question of, can we use zero-knowledge cryptography, that's what the ZK stands for, to actually build a better EVM? And if you're not familiar, EVM is the Ethereum virtual machine. It's the virtual machine or like the computer that Ethereum is essentially run on. And so the key question is, with all these ZK EVM projects, is Aleo a ZK EVM in and of itself? The short answer is no. But what exactly is ZK EVM? I think it's important for us to define that. So when we get into the part about Aleo, you can understand where the differentiation is. So I have this chart here, and when we think about what a ZK EVM is, the definition is actually a little bit broad, but I think this chart is a good way to sort of summarize some other projects that are building ZK EVMs. Again, Aleo is not one, but this kind of gives you sort of a general idea of what's going on here. So basically, it could mean a lot of different things. If you look to the far right, you can see what the definition of the EVM is, right? So you see it's Ethereum. And as you move increasingly away from Ethereum, so like all the way on the far left, you have Starknet, you actually become less and less compatible with Ethereum itself. So you sort of lose compatibility. So when you're sort of assessing the landscape of projects, the closer that those projects are to the Ethereum stack itself, the more compatible you get with Ethereum. You should also maybe, so it's not on this chart, but if you had an arrow pointing the other way, you could think about performance. So the farther away you get from Ethereum, the less compatible you get, but the more performant you get. And so, at least as far as we know, the closer you try to get to a ZK EVM model that emulates exactly what what Ethereum does, you essentially have to pay quite a heavy penalty in performance. And so this is why, like, if you look at projects like Starkware, their network's called Starknet, they have really, really high performance, but you aren't able to do a lot of the same things in Ethereum, whereas like Scroll, which is simply like a roll-up layer 2 solution, and we'll talk about that a little bit more, it's literally just you know, simply just trying to scale Ethereum, but keeping all of the core properties of Ethereum in place. And this mine space right now is very new, it's very nascent, so everybody's just trying to figure out, you know, what is the best approach to try and make the current blockchain ecosystem more scalable and more robust. And so that's kind of how people are using zero knowledge to, yeah, essentially make improvements and make, you know, Ethereum faster, more efficient. So jumping into this next slide, so what I just described to you is why we at Aleo actually decided to build a new model from the ground up with this exact use case in mind. So we want to be able to enable sort of, think about it like programmability of Ethereum with the privacy of something like Zcash, and like gain all these efficiencies that you would otherwise lose if you were using Ethereum today or one of these ZK EVM solutions. And so I would say we're not a ZK EVM, we're simply a ZK VM, because we've built our own VM using zero knowledge, but it's not directly associated with Ethereum, because at the end of the day, we wanted to try and circumvent the challenges that you have with Ethereum. And so the way our model works is that you have this high level programming language, which is called Leo. And like I said, one of our other colleagues will be doing a workshop on this later. And that compiles down into an intermediate representation called the AVM, which is the Aleo virtual machine. And there's actually like a language associated with that as well called Aleo instructions. And then that actually gets turned into AVM opcodes, which then gets synthesized into what is called R1CS. And R1CS is basically this cryptographic primitive that, you know, proofs are made of. So with zero knowledge, there's this concept of zero knowledge proofs, and we'll sort of get into that further. But that's kind of the very high level of how our model works. And you as a developer can use our Leo programming language to build your application and use and actually build with zero knowledge, which up until this point has been quite difficult. And so, okay, so why is this even a hard problem, right? Like trying to create this more scalable and private infrastructure. And why can't we just replicate the EVM exactly? And by the way, throughout this presentation, I'm going to cite a few people here. This information was actually from an individual named Gautam Botrel, who works at Consensus. I definitely recommend checking out some of his writing and his work. It's really great. And the TLDR is that the thing that the EVM reasons over are 256-bit words, and the operations there are bitwise arithmetic and Boolean operations proofs. And so what a zero knowledge proof is, it's a field element and or some group element of a field, which is typically a cryptographic field like an elliptic curve that I've shown here at the top. And what is a program in that model? Well, it's a circuit, so that's like the bottom image, encoded as a polynomial defined over a field. So these are two very different things, and typically when you try to translate that into the world of a regular computer program, as Gautam points out, typically the blowup is quite large. And in fact, there's actually already some research that shows you can build effectively a CPU inside of a zero knowledge proof, and it's called TinyRAM. I highly recommend people look that up if they're interested. And basically this blow up factor of any program is 10,000x in terms of the number of constraints, as opposed to if you just implement the program step by step. So I know that was probably like a lot of, maybe some people understood that, maybe some people maybe didn't click as much, but I think the key takeaway here is that essentially what zero knowledge proofs are doing, if I just had to put it in a couple words, is they are reducing complexity of running really complex programs on a blockchain. And I'll sort of, go over why that is. And I'm sure many of you probably know what some of those reasons are already, but that's sort of the key takeaway. We use zero knowledge cryptography to compress the complexity, which allows you to run programs more effectively. Okay, so this slide, this is just another way of sort of describing what I just talked about. The challenge here fundamentally is that you have an idea for, let's say you have an idea for a program you want to write in some high level language, right? And there's a lot of complexity behind it. I'll give like a very basic example. Let's say that I want to prove I know the sum of two numbers. I don't know why you'd want to do that, but just for the purposes of this presentation, we'll go with it. Basically, what you would do is you write it out in a high-level language, okay? And then what Leo and the AVM does, which I described 2 slides ago, is it compiles it down and manages this problem of basically efficiently translating between the world of zero-knowledge cryptography, or the cryptographic world, where things are all group elements defined over elliptic curves, like I said, with the world in which the program actually needs to be evaluated with what's actually being computed. And to do that efficiently is why we built our stack from the ground up. And this is why you kind of see all these different flavors of some of the ZK EVMs that I had mentioned earlier. So again, really what we're just trying to do here is abstract away all the complexity so that all of this complex elliptic curve cryptography and this jargon that I just mentioned right now, you don't need to worry about. If you program in Leo, it's designed similarly to a language like JavaScript or TypeScript. It's very straightforward, and you can just start building your application using the syntax that we've designed. Because up until this point, if you wanted to build with zero knowledge, you would typically have to be like a Rust expert, or you'd have to build your own circuits, and it just gets very, very complex. So again, if you just want the key takeaway there, it's essentially that we are abstracting away all this complexity for you to run some sort of program and prove the output of it. Okay, so again, this is another model of how Aleo works, just kind of another visual here, and we'll go through this in a little more detail. But the point I want to make quickly is, so today we have Leo, right, which I mentioned before, which is our DSL/compiler that compiles to the AVM. And then we have Snark OS, which is basically our layer 1, where we have validators that also serve as verifiers and can verify transactions where computed correctly. And the point I want to make here is that we have Leo that targets the AVM, but maybe in the future we could have other languages that target the AVM too, or even potentially a transpiler that targets Leo or the AVM directly. So there could be a world in which you could write Rust or Solidity or some other language, and maybe through some transpiler architecture, you can just basically end up still being able to do all of this, all the same things I described before. And this is kind of interesting to go for like a future direction. And this is very similar to the definition of the EVM on the far left in that chart I showed earlier. Or sorry, the EVM on the far right, excuse me. And this is what Aleo could potentially someday look like. So really, we want to be as modular as possible. We have Leo, Leo is going to evolve, independently of our ecosystem. And we'll kind of see what people end up using Leo for. But at the end of the day, we can have any program language compiled down to the AVM and then subsequently to our layer 1, which is our operating system, Snark OS. So I think that's actually a really cool concept, and it's something that people in our ecosystem have been exploring. And I know a lot of people were interested in understanding if we had like a JavaScript SDK that could do this, and it's something we definitely want to work on. So yeah, I think the analogy I just want to point out here is our program is very robust. Okay, so going back to this question, is Aleo a ZK EVM? And I just gave you some more information on kind of the flavors of ZK EVMs and how we're working. Maybe? Okay, so we said no earlier, but maybe, like after I gave all this information, it's like, maybe it is. But still not really. I would say no, it's still not a ZK EVM. And so what? What's the point? It's like, what's the whole point of a ZKM, and why do we even care about this? And why is the EVM important? All these things. Like, why do we even care? So the EVM is important because we want to be able to compute general programmability on chain, and that's something that was novel with Ethereum. And in the next slide, I'll kind of go into that a little bit more, giving you a bit of a history lesson of how we got to that point. And I would define Aleo as a platform that uses a ZK VM. Again, the E part here I think is extraneous because what we ultimately care about is computing programs on chain using zero knowledge. We don't necessarily need to use the programming model of Ethereum. It just so happens that Ethereum is sort of the go-to platform that a lot of people are building on, and so it has like a lot more support and traction than a lot of other platforms out there. So, I'm a big history guy, so I really wanted to have this slide in here. And basically, I'm going to take a bit of a digression and tell you a little bit about Aleo after this quick historical overview, because I just want to acknowledge that, and the first thing actually I want to acknowledge before I go into this, because we have this timeline of different projects, is that Aleo is not an Ethereum killer, right? It's not a Bitcoin killer. It's not a Solana killer. It's not an anything killer, right? We're not trying to eliminate any of these platforms or necessarily replace them. Aleo represents a step along a path that had many prior steps before it. And I think it doesn't get acknowledged often enough, especially in the modern world of crypto, where things move so fast. But people have been working on trying to make digital money for like the past 40 years. And there's been a ton of failed projects up until Bitcoin. And all those failed projects in the past, here I have DigiCash, but there were even some more before that, eGold, Hashcash, all these different things. But they ultimately inspired Bitcoin to do it the right way. And the key insight with Bitcoin was actually not cryptographic at all. It was crypto-economic. So essentially this concept that you have miners, right, if you understand like how Bitcoin works, and you're able to build an incentive structure in a certain way that actually aligns all the incentives of the participants in the network along with the miners. And the whole system in this case is then able to work trustlessly and permissionlessly. And so Bitcoin inspired a lot of different directions from the same kind of turning point. And then Ethereum, similarly, Vitalik and others, they took the insight from Bitcoin and were like, okay, well, we have Bitcoin and it's really cool, but it's not as powerful as it could be imagined, right? What if we took a computer and we put the computer on chain? And if you go back, to 2015, 2016, 2017, you see all these different projects that take that idea of having this computer like on chain. And yeah, if you move to the right in this chart, you kind of see various projects going in all different directions, whether it's Cosmos, Near, Solana, whatever. But Ethereum sort of started that initial trend. Again, having this on-chain virtual machine model. And so Aleo, we kind of see as the next step down this path. So we're trying to implement a model which is based on some research that was actually authored in 2018 called Zexe, which is spelled Zexe. You should definitely check it out if you have time. I think we included it as part of our resources for the hackathon. And the idea of this was to try and combine some of these past approaches and, accept some trade-offs to essentially have an off-chain computing environment where you compute program transitions off-chain, right? So that's kind of how Aleo works. And then you actually verify those transitions on-chain after they've been computed. And so this is really good for scalability. And we view this as a step in a different direction that gives you some kind of new capabilities and powers. So again, you run a program off-chain, you generate a zero-knowledge proof, right, of these state transitions of the program, and then the zero-knowledge proof is what gets uploaded on-chain. So you're getting a lot of scalability there, which again, we'll kind of go into why that is. And then on top of that, you get privacy, which again, we'll talk about further, because zero-knowledge proofs in and of themselves, they don't give any information about the program that was run. And like I said, we'll try to cover that further. Okay, so in this slide, I just want to maybe highlight some of the key features of Aleo that are really cool and interesting, I think, for developers. And essentially, maybe I'll start by going back to Ethereum, since that's probably what people are familiar with. So in Ethereum, you have this excuse me, you have this concept of gas, right? And you need gas. Why do we need it? Well, the purpose we need gas for in Ethereum is to make sure that no one can force the EVM into an infinite loop. And so gas is there to make sure that effectively no one can DOS the system, denial of service attack the system. And that's because every node on the network, this global state, is executing every single transaction to verify that it's correct. And that's extremely cumbersome. And if somebody just kept flooding the network with transactions, nobody else's transactions would get processed. And that's why you need these gas fees. In the world of zero-knowledge cryptography, the beauty of this is that you can actually cryptographically prove a statement without revealing why it's true. And if you accept that proof, you know that only honest verifiers will always accept that proof is valid, and therefore you don't need to actually re-execute the entire instruction of the entire program. So that's really cool, and makes for much better efficiency. And also the additional thing we're going to talk more about, we'll talk more about this later. And yeah, I think this is like a really underrated insight. And it actually allows you to have this concept of like unlimited application runtime, right? Because we don't have to do all of this re-execution as you have to do in Ethereum, for example. And maybe one other thing I'll point out just to do some comparisons here. So the stack size of Ethereum is actually 24 elements. So theoretically, you can write a smart contract in Ethereum that would overflow the stack size in that theorem. So there's actually a limit, effectively. And I don't think for most programs it's of any practical importance, but the important thing to note is that there is a limit into what you can do or what you can actually run on Ethereum, right? Like you can only get to a certain level of complexity. And that's why with all these other ZK EVM solutions or rollup solutions, they're trying to make it so that you can have more complexity on Ethereum. But in the Aleo model or in the ZK VM model, you don't have this limit because you're running a computation entirely off chain. And I'll just give like a example here. I don't know why you would want to do this, but you could basically do a protein folding algorithm for years. And actually at the end, you can come up with the result in the form of a zero knowledge proof. And then you can present that proof as being valid, which I think is like really interesting. So again, you don't need to have all those computers re-execute that really long protein folding program. All they have to do is check the zero knowledge proof, which is a much smaller piece of output that they're looking at. And in this chart here, I basically show like a mishmash of things, but I think the key thing to take away here is, again, zero gas fees needed, kind of like I was explaining, unlimited application runtime. And then on the left in this chart, I think another way to conceptualize Aleo, and I'm not sure if I mentioned it in the first slide when I started presenting, but we're just trying to take the programmability of something like Ethereum, so the ability to write these, more complex programs, and combine it with the privacy of something like Zcash, where Zcash was just private money. Whereas here, we actually want people to create private applications. And maybe just quickly, some interesting use cases around that would be things like, privacy preserving DeFi, identity use cases, private DAOs, voting, right? Like everybody in the US is so concerned about voting, right? Imagine that you could basically prove that, okay, we have X number of votes for candidate A, X amount of votes for candidate B. We know that there was no double voting, and we can validate that all those ballots are legitimate. But we also don't need to reveal any of the information about the individuals that voted, right? So I don't need to trust some ballot counting agency that they did it correctly. There's actually a global state that anybody can check to say, okay, here's the total number of votes. They're all legit, but we also don't need to tell you who voted for who, right? And I think that would actually help people, because a lot of times people don't like to discuss politics or like share who they voted for. And then also gaming is like another big area as well. There's been a lot of people from the gaming side, they're interested in using zero knowledge to run their more complex gaming applications for scaling purposes, and actually using the privacy preserving aspect to create like cool in-game privacy preserving primitives. So yeah, I'll just maybe jump ahead a little bit here, but like I was saying, we're sort of an extension of Zcash for like the privacy aspect of it. So if you think of the Zcash model, you have records, and these records are basically the fundamental unit of data on chain. And then the way state updates happen is people prove that they have ownership of a record, that the record exists in one, in one of these specific data structures, and that they also have the key that allows them to spend the record. So you can basically use that to create a system of payments, right? So there's a transfer, there's essentially like a transfer of value. And this is actually exactly how Tornado Cash on Ethereum works. And by the way, the XE model I mentioned earlier is the exact same thing, except instead of just payments, there's this additional parameter that are in a record, which is known as a program ID. And this opens up the door for being able to have user-defined predicates to essentially, like, again, allow you to do more complex programs instead of just, okay, I pay you, you pay me. You know, we can have more complex logic, which open up the floodgates for some of these more interesting applications just outside of like private payments. So yeah, and essentially, like, looking here, just to go through like the process of how we work at a high level, you have like this one-time setup of the system in the beginning, where you generate all the parameters you need to prove and verify, and then you have a prover, and we'll talk about that a little bit later. And these are different parties in the system. And then the prover basically takes some public states, private state, and a user signature would then generate a proof and submits that proof to the chain. And so you have a separate party, and then you also have a separate party, which are validators or verifiers in our system on chain, and they verify these transactions and update the state. So essentially you have like these developers who are writing programs, right? You have these provers that are running those programs, right, by generating zero knowledge proofs. And then you have verifiers that are updating the state on chain and verifying the transactions. So I think, yeah, the really, I think, cool part about this is the provers, and I'll talk about that a little bit later. But that's kind of just, yeah, sort of the high level of how we work and how it's been extrapolated from like Ethereum and Zcash, like taking some of those original principles. And so here's like another slide to explain this. Maybe this is a bit simpler of a diagram, maybe just a fancier way to visualize it. So once again, just to reiterate, we have developers in our system, which would probably be you guys, like people in the hackathon that want to write applications. You'd be a developer. And at that point, it's just like Ethereum, right? So these developers in Ethereum, you deploy a smart contract. In our model, you have developers, they would deploy what we call a program, but it's kind of the same idea. And you deploy it to actually an on-chain program registry. And so this on-chain registry, developers can deploy a program, and those programs will get compiled to AVM bytecode that corresponds to the logic they actually wrote in their application. Okay, and then what happens is the provers, they receive a transaction request from a user. Again, you could be a prover, or this could be outsourced to a third party, right? So you don't actually have to run a prover on the network. If you're just an individual user, you would pay a prover a fee to generate a zero knowledge proof for whatever application you're using. And so they do that. So they take the AVM bytecode and some initial parameters generated during the setup, which I mentioned earlier. You synthesize all that information together, and that's how you actually generate the zero knowledge proof. And then that zero knowledge proof gets wrapped into a transaction, gets submitted on chain, and the state updates occur via the validators. And then you just have this cyclical pattern. So those are kind of the three main parties that are involved in our system and kind of how it works. So again, going back to the comparison of Ethereum to Aleo, just to give people sort of a visual. So actually it's kind of similar to the way like rollups work, I think, in a lot of ways. So, you know, nowadays there's this concept of modular blockchains, and a lot of people have talked about this. And, you know, in a rollup, it's kind of the same idea as like a modular blockchain, right? So you're essentially separating. So again, I'm talking about rollups here, and a lot of people have probably heard of these projects building rollups. So essentially what you're doing with a rollup is you're separating the execution from the settlement effectively, right? That's why they call it a rollup, or like a layer 2 solution. And so this is exactly what we do in Aleo, but we just do it natively, right? There's no rollup concept. It's all native to the system itself. You don't need another layer. So in Ethereum, you have developers or users. They're submitting intents to rollups, basically signed, and saying, you know, hey, I want to transfer from A to B. And then the rollups execute these intents, and then the validators on the layer one, they verify these intents were executed correctly. And this is the exact same model that we follow in principle, although again, it's a different architecture built from the ground up to be much more efficient. Like I was telling you before, right? Because if you're trying to get closer to Ethereum one-to-one, you're more compatible to the Ethereum ecosystem, but you're less efficient. And we'd rather have much more efficiency. Okay, so I kind of went through all of this. I won't spend too much time on it, but kind of just another visual. So let me just say one quick thing about what makes the architecture in Aleo different. I know I've been, talking about this in a lot of different ways, but maybe just adding on to it here. So, so when you deploy a program in Aleo, you deploy to a program registry. I mentioned that before, and I think that's a key differentiator. But what does that mean, though? So effectively, there's a namespace that exists on chain that's tracked by all the validators, because this is exactly how you know what program you're interacting with. Because if I just gave you a proof, you don't know what program it is, and it's impossible to reason about a state update, right? Because the zero knowledge proofs, they don't give you any specific details about the program being run. So this is kind of an interesting thing, and opens up a lot of doors to potential applications. So you could have a namespace and put everything inside the program ID. So in addition to being useful for programs, it could also be useful for identity applications or other things like that. Like maybe just giving a tangible example of an identity use case. Imagine being able to log into a website without entering a username or password. That's actually a pretty cool concept, because if the website got hacked, your information would never be compromised, right? Because all that the hacker would access is some zero knowledge proof, which doesn't give them any information, right? It's just a random, cryptographic statement or proof that says oh, X user owns this account. But we don't even need to give the name of the user, in fact. They literally get nothing. But again, we can only enable that by having this program registry, because the validators still need to prove that okay, these proofs are correct. And so, that's why we need to have it sort of contained in this registry. Cool. So then, okay, we have this concept, and then we also have this concept of callers and provers, where if the caller calls a prover to execute some function, again, in the real world, okay, so these are computer science concepts. So if we're just separating these two agents, in practice, you could be the caller and the prover. There's no reason why you couldn't synthesize your own proof yourself. And I think it's very important, because it implies decentralization. But I think decentralization is a very worn out word in the space. I think more importantly, it implies permissionlessness. So you don't need to ask permission for anybody to deploy a proof, which means there's a lot more opportunities to potentially compose and combine things. And then, I kind of went over validators, so I don't think we need to jump into this too much. But again, the validators, it's more of traditional proof of stake based architecture, which maybe some of you are familiar with. Okay, so that's what it looks like in summary. So let me just restate it all again from the beginning. So again, Aleo is building a new layer one blockchain using a proof of stake architecture, right? That's our consensus mechanism, based on a variant of hot stuff, which for any of you familiar with that consensus algorithm, it uses a computing model based on Zexi, the research paper that I mentioned earlier, which is a ZKVM, right? And in that model, it's defined by off-chain computation, which I mentioned as well, featuring unlimited runtime, where transactions are proofs, and then these proofs are submitted on-chain, where validators verify these proofs are correct, and they never have to re-execute them again and again. They never have to re-execute them again and again. And so, this and this architecture itself also allows us to preserve perfect privacy. Again, because the zero knowledge proofs themselves, they were generated off chain, and the proof doesn't actually show any information about the transaction that was facilitated. Okay, so what's good about this? So this is called decentralized private computation. It's actually a term from the 2018 Zexi paper. I think that's honestly the coolest thing about it, right? About this whole concept. And this primitive in general is extremely exciting because for the first time, you have this permissionless system where you can deploy programs and interact according to the logic of those programs privately on chain. And so we're really excited to launch this potential new paradigm. And so, you know, I'll try to go through that in a little more detail. I've talked a little bit about these points and like why it matters and who cares. But yeah, I think in general, we've been to like, maybe some people have been like involved in the Ethereum ecosystem, maybe not, maybe making an assumption here, but if you're in the Ethereum ecosystem, you know that scalability can be challenging on Ethereum. And one of the reasons why scalability is challenging is that, again, as I mentioned before, every single node has to re-execute every single transaction. So this is why rollups are oftentimes looked at as a really promising architecture because it separates those two things, right? So when you separate execution from settlement, you get greater scalability and efficiency. And so, yeah, basically this is just an image to demonstrate that, right? You get more efficiency. But yeah, I think in general, that's like one of the most exciting things about our platform is like you get the scalability and efficiency, and you don't need to rely on the trade-offs that are associated with Ethereum. And in Ethereum, you can't really do privacy-preserving applications either. So that's sort of another thing as well. So it's the combination of those things. And so yeah, maybe here I'll just cover this briefly, but again, Aleo is a proof-of-stake blockchain, and I was talking about efficiency just a second ago. And I already talked enough about how when you're a prover, you execute a transaction, and it only needs to be verified once as opposed to forever for all time by every node. But one of the things that we have implemented, which I think we're the first team to actually implement, are frost signatures for our consensus algorithm. And this is what validators use in the process of consensus to sign or validate blocks. But users or developers can also take advantage of this paradigm. And Frost is basically a threshold signature scheme using Schnorr signatures, which recently got integrated or is being integrated into Bitcoin. So for those who aren't familiar, Schnorr is a really nice, efficient signature scheme. In general, Schnorr is actually a zero-knowledge protocol called the Sigma protocol. And the point here being that, you know, it's much more efficient to aggregate several signatures together, and it's also cheaper. And so this is a way in which you can do things like multi-sigs in a way that's, again, much cheaper. And in terms of constraints, you know, there's much less constraints than in other systems. So yeah, for anybody who is curious about that, we're like the first team to be implementing this threshold signing with Frost signatures. And then I guess the other thing I'd like to point out is, you know, the cryptography as a whole that we're developing in this system, right? Because, you know, this is a big part of what we're doing at Aleo. And so we're essentially developing new ways, you know, to make these cryptographic processes faster and faster. And every year, thanks to contributions from many people, you know, these proof systems are becoming much more efficient. And there's one in particular called Marlin, which I should have probably mentioned before, but we use Marlin in Aleo, this proof system. Again, it's a universal zero-knowledge proof system, which means that you can basically, you know, prove up to a certain size, like any kind of logic. And so this is a relatively recent phenomenon, and I would guess since the post-2019 era, originally Marlin did not integrate any kind of lookup table, which is a feature of another proof system called Plonk. And so one of the things we're excited about is that we're integrating kind of the best of both approaches here, and we're taking the lookup tables from Plonk and we're integrating them into the Marlin proof system to get much greater efficiency. This is important, I guess, for those who aren't familiar with Plonk and like why lookup tables help a lot. So there's a certain operation I mentioned a while ago where computers reason about programs and bitwise functions, you know, arithmetic and integers. And then there's cryptographic elements to translate between those things for certain operations. And it's really expensive, for example, like SHA hashing, you know, like SHA-256 in Ethereum, for example, is very costly to do inside of a zero knowledge proof because it's two different things. But you could actually integrate and implement a lookup table and make it so that you can get the cost way down when trying to compute those two things together. And basically, yeah, it's used to pre-compute expensive functions and then, again, just make things much cheaper. So I guess the key takeaway here is Marlin, really cool cryptographic primitive. Then we also have like these lookup tables. The two things combined together make cost really low. And then the other thing that Marlin gives you is batch proving. And this is actually very similar to how rollups work. So in Aleo, every transaction can consist of 264 separate state transitions, and these are batched together in a single transaction. And the cool thing about this model that we have using Marlin is you can batch these together in a way that the cost increases sublinearly with the number of transactions. So you know you have a single transition and you can get the cost on that like pretty effectively. And the higher and higher or closer you get to 64, it increases sublinearly. So it kind of encourages you to batch things together, and it makes it even cheaper for a prover to ultimately compute. And I think that is like super important as well. Okay, so again, I wanted to go back to program runtime and why this is potentially cool and important. So I gave a couple examples, but another example that I think is really cool that no one has talked about before is machine learning, using machine learning to potentially to define some program logic you could imagine. And so actually, let me think. Backing up here a little bit, you can actually do an ML model on Ethereum, like a linear regression, for example. But the problem here is if you try to do something like that, it's quite expensive again, because of the gas limit that we talked about. And again, we have unlimited runtime here. So ML applications are actually fine to do in ZK. And in fact, there's a lot of really cool, interesting applications that we have been kind of talking about around, proving the output of like these machine learning algorithms, for example, to define like a bonding curve. So again, the unlimited program runtime, enabling sort of applications around machine learning, for example, I think is something that's really great. And so, yeah, I think this is just another visual show here. And yeah, so here, I think I covered this as well. And I do want to leave time for questions, so maybe I'll just skip over that. But again, I think the important thing is in every block on Aleo, the on-chain execution, so outside of Aleo, on-chain execution limits application expressivity, but on Aleo, that's not the case because, again, you're doing most of the computation off-chain, and then what's being uploaded on-chain is just a zero-knowledge proof. And this visual is explaining like how you have limited runtime, stack size, and storage for other programs like Ethereum, for example. Okay, cool. And so another what's good about this as well, so the privacy aspect, and I think this is actually our biggest selling point. So privacy is an interesting topic in this space because a lot of people feel very differently about it. I think, for many applications at scale, privacy will be absolutely essential. I mean, if we think about the model of blockchains in general today, it's actually shocking how transparent they are for most financial use cases. I mean, if I send, I'll give an example. If I send you money to your bank account, when you give me your bank account number, okay, maybe I know that bank account number belongs to you, but I don't see how much money you have in the account. I don't know what you spend your money on or anything like that. The bank does because they're facilitating the payment, but I, as the sender, don't see any of that information, nor you as the receiver see any information about my account. In crypto and blockchain, if I give you my wallet address, then you can go to a block explorer and you can see how much money I have in that account, where I've spent that money, and then you can actually backtrace and see like, oh, who I've sent to, and then you can go to that person's wallet and you can start making all these correlations, and it's fully publicly viewable by the entire network. But if we want large scale adoption, what would be really cool is if you could have a block explorer where you can record the fact that a transaction occurred, represented as a zero knowledge proof, and that it was valid, but and the world can see that, but we don't need to see all the specific details about the transaction itself. And so again, Aleo sort of enables that, and I think that's super powerful. So yeah, we're guaranteeing privacy, so users only have to share what they want. I think in this slide, essentially what I want to point out is that we're a private by default platform, which means you as an application developer, when you write your program, everything by default is fully private. Then you have the option to decide, okay, what aspects of the program will be publicly viewable, which is really good for regulation, especially with the fallout of FTX recently. Trying to be regulatory compliant will be super important. And then again, you as an end user, either sending or receiving money or interacting in some way through various applications, you can decide what information you want to selectively reveal as well. Whereas the default in the current models is that everything's fully public, and then you can't really go back and make that private. So yeah, that's kind of the model we're working on. And for applications like Zcash, you know, they're the opposite. You have to opt into privacy, right? We're private by default. So that's kind of a difference there, which I think is important to highlight. Yeah, also, so this image is just for any of the developers in the room. So this is Aleo instructions. This is our intermediate assembly-like language. So this is not Leo. Most people will build with Leo. And again, the workshop on December 12th will be focused on that. But this is our intermediate language. It's more assembly-like. You can build with it. But yeah, if you're curious, yeah, what the syntax looks like, you can check this out on our GitHub repos. And yeah, we can basically output public and private values, as you can see kind of listed here. But just wanted to give you a taste of maybe what this looks like. And so yeah, the second to last point on here on why our stack is good. So we were able to incentivize provers to run better, faster, more efficient hardware. And so I'll go into that a little bit as well here. So essentially in our system, so the provers that I talked about earlier, their whole purpose is to run applications on the Aleo network. And we actually have a system set up such that we're incentivizing those provers to create better physical hardware and optimizations for generating zero knowledge proofs, because right now it's super inefficient to generate a zero knowledge proof and it's quite costly. And at the end here, I'll talk about this initiative that we launched called Z-Prize to try and help with this effort. But in short, we developed this system using a mechanism called proof of succinct work. It's kind of a hybrid between traditional proof of work and this theoretical concept known as proof of necessary work. It's not part of consensus, right? The validators do consensus, but this mechanism is still there to incentivize people to create better hardware, because essentially we'll be creating this entire third-party marketplace for people to generate what we call proofs as a service, and people will have to compete against each other similarly into Bitcoin, how miners have to compete against each other to generate the zero knowledge proofs. And hopefully that will like set market prices for, you know, fees for generating proofs, and also incentivize people to create more efficient hardware so they can compete. And yeah, we could have a whole talk on specifically how that works, but it's very similar to proof of work in Bitcoin, but instead of grinding SHA-256, you're grinding snarks, which is the implementation of zero knowledge that we use. And yeah, so the one other thing is like we instituted this Coinbase puzzle. So like I said, it's proof of succinct work based, and yeah, minimizes proving parts to achieve a puzzle that is robust to amortization, achieve smaller proof size, right, than the existing Marlin-based proof of succinct work, and it's capable of aggregating across provers easily, right? So the entire setup is basically meant to, yeah, create this more efficiency. And the Coinbase puzzle is, it's essentially our mechanism where people have to solve this puzzle. It's not related to Coinbase, the company. It's just called the Coinbase puzzle, right? You solve this puzzle, you generate a zero knowledge proof, you collect fees from the network, and then you also collect fees from people who need a zero knowledge proof generated. And so yeah, the last point here I want to say, why is all this good? It retains composability. And I think, yeah, the cool thing here is, you know, we can take what different people have worked on and combine into something which takes the most powerful aspects of all these different crypto architectures into one really robust system. So composability is super important for, you know, having an effective blockchain system in general. And so We think that that's like a really important point. I just want to go through here. Yeah. So again, retain composability. I think that's super important. And yeah, the last thing I'll say here, there's not a silver bullet for apps that require concurrent state access. Yeah, just another important point to highlight there. You know, I think the reasons why Aleo is amazing and why zero knowledge is amazing is not yeah, it's not simply just trying to use it for like scaling solutions on Ethereum or some of these other platforms. Specifically, I think it's just better for getting more privacy and having a lot of this robustness, which we're trying to build from the ground up. I'm gonna make sure I only have like 10 minutes left here, so I think this is like the last three things. So maybe I'll just leave you with our testnet 3 launch plan, and please excuse the dates at the top. Those were, with any crypto project, we always put dates on things, but then we gotta change them, so you can ignore that. But basically, right now we're running our final version of the testnet 3. This will be burning for mainnet launch. We're targeting mainnet end of Q1, early Q2 next year. And essentially, there will be multiple phases. So this first phase, people will be able to write and deploy applications on the network. We've gotten the part where people can write applications, but deploy, I think we're actually pushing back a bit, but you can actually still deploy locally. So if you want to go on our testnet and write an application, you can. The second phase, which actually did launch, so this is launching our provers. So this is the Coinbase puzzle part that I mentioned. So generating zero knowledge proofs and running programs, you can actually do that right now. So that's super cool. And then the last phase will be running the validators, right? So they're verifying transactions on chain using our Aleo BFT consensus mechanism. That has still not been launched yet, but should be launched, I think, shortly after the new year. And once all these things are launched, there will be incentives kicked in on the testnet. So if you want to participate, get testnet tokens. So when we launch mainnet, you can claim them. It's possible you would have to KYC. That's the only requirement, just because it's pre-mainnet. So yeah, we're essentially assigning value to a token that doesn't exist yet. But that's essentially our testnet launch plan, and it would be great for people to get involved in that. And the last thing I'll mention is check out zPrize. This has to do with hardware acceleration. So if you're interested in that space, it was a joint initiative we did with a bunch of other projects, building with zero knowledge, and we're actually releasing all the output from that. And again, this will help to even the playing field for people that want to run provers. And all the output from this initiative will be open source, so anybody can benefit from the research from this, and hopefully it will help spur forward innovation in ZK-based hardware. And then, we also had a setup ceremony. I think we had like the most contributors to date. And this setup ceremony, as I was showing before, was used to generate the initial parameters for our system. So you can definitely check out stats on that if you're interested in seeing like how we conducted our ceremony. And so, with that, I will leave it there. I know we only have 7 minutes left, but if there are any questions, I'm happy to take them. And I really appreciate you guys giving me the time to talk today.
Wow. Thank you so much, Anthony. That was fantastic. I know it was very comprehensive and a lot of information, but a lot of really, really good information. And it just gives everybody a very clear idea of who Aleo is, what they're doing, and where they're going. So, I can say we really appreciate you, man. As far as time, we're good as long as you're good. So, if you have a hard stop, let us know. Everybody in the audience, I mean, there must be some questions out there. I know I have a ton. So if you guys want, please raise your hand in the audience for anybody who has a question, or pop it in the room chat. We'll give you guys a second to raise your hands. And if we don't see any raised hands, I'll start asking questions.
So I see in the room chat, somebody said, this is very exciting, use cases. I didn't really... this talk was a bit more technical. I wasn't sure how high level to keep it, but use cases. So I think some really, so I kind of mentioned it earlier, but some interesting categories are, and all these use cases, it's applying privacy to them. So one is DeFi. So like, let's say, for example, you want to trade on-chain derivatives, but we need to assess your creditworthiness. You could actually create an application where we can prove that you have a certain credit score, like a certain number, but you don't need to give us like any more information, because you can just prove it using a zero knowledge proof. And I think that's like really powerful. Or like, yeah, if you want to do like a dark pool or a mixer, something like that, like a private exchange, you could do that on Aleo. Identity use cases are a big one. You know, the funny example I like to give is, you know, if you want to prove you're 21 at a bar, how do you do that today? You give somebody your license, but your license has more information than just you're 21. It has your name, it has your birthday, it has your address. Imagine being able to prove to somebody and not even telling them your name, I'm 21. You can validate it via this proof. I own the proof because I have the keys to it, right? The private key, or in our case, the proven key. Basic stuff like that. You know, zero knowledge authentication. So like I said, logging into websites. Gaming's a really big one. So maybe for like Dark Forest, that was sort of an initial stab at using ZK for that. And then, yeah, voting, I'm really into the voting one, and like governance for DAO infrastructure. And then I think machine learning is a really big area. So being able to prove that the output of some algorithm was correct, doing that more efficiently by, you know, using a zero knowledge proof, and then also having it so you don't need to reveal the data that was actually used, you know, that was run through the algorithm, right? Because you can, yeah, have that remain private. So those are just some examples, but I think, yeah, those are the most interesting to me. I'm a big privacy freak, right? Like my girlfriend makes fun of me all the time. You know, I have burner phone numbers. I never, yeah, like I'm just very like precautious about this kind of stuff. Like I'm always cautious when I fill out forms online. Whenever I book a reservation for a restaurant, I never use my real name, like, because people are just collecting all this data and information, and you're just giving them more and more and more. But with Aleo, like with private identity use cases, you can actually maintain control over all that information, and you don't need to necessarily give like every detail of your life to all these people just to validate who.
So let me if there are no hands raised, I have a couple questions. You
Sure.
may have answered them. I was multitasking, so if some of them are redundant, just say so. That's fine. So how do we, or I should say, how does Aleo determine honesty in a verifier? Because in my mind, you know, fundamentally in any network, right, there becomes a point. So how do we maintain that a validator is honest in the perspective of Aleo?
Yeah, that's a good question. So basically, yeah, just to recap, it's like you have the developers on the network, they'll like, you know, build their program, whatever. And then that's also kind of the point where users would interact. Like if you use some application, then you have provers, they run those programs, and then they also generate like the zero knowledge proofs for those programs. And then the validators, like those would be the people like verifying the transactions. So they are the ones that like take the programs that were run by the provers in the form of a zero knowledge proof, and they basically validate that. The way that they're kept honest all has to do with like Aleo's. Yeah, sort of. So it's like a combination of our consensus mechanism, which I kind of touched a little bit, but I didn't really dive into like super in depth. But like the Aleo BFT consensus mechanism.
Mm-hmm.
They're incentivized to be honest because it's like a proof of stake network, because so they have to like stake their own tokens like in order to validate transactions. And if it's deemed that like by other verifiers on the network that you know, they weren't being honest actors, then they'll get like slashed, and those tokens will be, you know, taken from them. Okay. So that's like one piece. And then the proof itself, the way it works is like there's a prover, right? So you have the provers on the network, and then you have the verifier. Again, you could be the prover yourself, or you could just have this outsourced because maybe you don't want to handle it yourself. The proving key is able to, the prover uses the proving key to basically like do this cryptographic magic without getting into too much detail about it, to say like this zero knowledge proof is in fact correct. And then the verifier has their key to like see that output, right? Because anybody else who looks at this zero knowledge proof, it doesn't look like, it's just a cryptographic, you know, statement or whatever. There's no information behind it. So that's at like a high level how it works. Now there is a problem with like data availability. So it's like, how do we know the program off chain that they generated had the right data being put into it? That is a problem some people are trying to work on. There's this concept of like ZK oracles and a few other areas, but it's definitely still an area that needs to be explored. But if you can assume that the data input to generate the program off chain was fine, then you could make it work. So in that case, like maybe you wouldn't be getting, maybe your information would be somewhere out there in the world, but you're reducing the surface area with which it could be exposed, because it's like we only pulled it from one source. where it was originally housed. We use that to create the proof. But then now that we have this proof, whenever we want to share with anybody else, we don't actually need to give them all the information, right? Because that's how your information gets leaked, right? Because it's posted in like 30 different places and not just one.
Yep. Cool. Okay, I'm just going to double check for some hands because I definitely have more. Is it fair to say that, you know, the network is proof of stake, but the computational aspect of it, which is off chain, is still like proof of work, right? So the work's happening off chain, but the network is a stake network. Is that a correct statement?
Yeah. So the consensus mechanism is proof of stake based. It's Aleo BFT. So it's kind of like it's not straight up vanilla proof of stake, but it's a version of it. And then the computations that are, so when you run a program off chain and you generate a zero knowledge proof, that's where you use the like the Coinbase puzzle mechanism, which is the proof of succinct work mechanism. But again, that does not contribute to consensus. It kind of just, it still operates the same as like
it's just
hybrid of proof of work, proof of necessary work, but it doesn't contribute to like the network coming to consensus. It's just for generating the zero knowledge proofs, which happen off chain. Because if you did all of that on chain, it would be like very intensive and inefficient.
Yeah, I was just going to ask kind of back on the use cases side of things, especially in regards to the hackathon. Are there any projects in certain spaces that you're really interested to kind of see unfold? Or
yeah, we have a number of projects building right now. I can actually, we're still trying to organize like a lot of our resources, but there's this repo. Let's see if I can post in the room chat. Oh, I need to verify my phone. Okay, I guess I can't do that. I'll send it later. But basically, there's this GitHub repo. If you just Google awesome Aleo and then Howard Wu, our CTO and co-founder, you should be able to find it. But basically, there's a list of applications on there. I'm really excited for identity-based use cases, kind of like I said before. So there was one project that was working on creating like verifiable credentials. So basically, I can prove my identity without needing to reveal like all my specific details to somebody. That's like a really powerful one. It's not new ID, but I have heard of that project before. Yeah, but there's a team working on it. Also, like a lot of gaming applications are pretty interesting as well. Like we have a team that's working on this version of Liar's Dice where they actually implemented a bunch of like ZK privacy preserving primitives and actually changes your entire mindset of how you play the game. Or like if you did like zero knowledge poker, right? Like when you have to reveal your hand to somebody like after a round, like imagine you could prove who the winner was of that hand, but we didn't actually need to see whose cards was there. Like there's these interesting like game dynamics that can be made there. So I'm really excited for those sorts of things. But definitely the like anything around the identity space is probably my favorite area. Again, just because from a personal perspective, I'm really into that. And then one other one is the voting use case I really like. There's this project called Macy Minimal Anti-Collusion. I forget the I part. But Vitalik has been talking about building it on Ethereum for years. It just hasn't been possible. But there's actually a team building it on Aleo, which is a good case to show like, oh, here's something you could do in a private environment that you couldn't do on Ethereum. So yeah.
To piggyback on Sean's question about projects, actually, so have you guys implemented a granting arm yet? If so, if one was interested, what are you guys looking for and how does one get involved?
Yeah, sure. So we do have a grants program. We're going to be advertising it more coming soon. But if you want to find out about it, I will, because we don't have like a web page or anything. We're actually going to be launching this in the new year. But basically, if you go to aleohq.typeform.com/grants, you can apply for a grant if you're interested, or you can just go to our Discord and ask about it, and we can provide you the information there. So you just go to aleo.org/Discord. You can find information. So that's what I would suggest on that front.
Well, Anthony, thank you so much. Thank you everybody for attending. This was fantastic. We'll be posting the recording for those of you in the hackathon. We appreciate you, man. Thank you so much, and we'll all be in touch soon.
Yeah, thank you.
Thanks.
Really excited to see what people build.
Cool.
All right. Bye, everyone.
Have a great one. See you guys.